Wonderful. We're recording. Okay, so what are we doing today? Well, the topic for today is what we call data structures. Let me scroll all the way up. And in terms of the general topics we're going to cover right now, I thought this would be helpful because I rewrote this recently. The first topic is a kind of meta topic, which is why are we even teaching this at Code Platoon? What are we teaching and why are we teaching it? And that's important because everything else you learn, like, for the first 2 weeks, you're kind of learning these like essential language type skills. And week 4 and on, everything you learn is something pretty practical that helps you build a web app because the goal of Code Platoon is that by the end, you have a single full stack skill, which is in this case, web development, which is generally the most accessible first skill you could have, but you can branch out from there. But the idea is you need to learn a fair number of things to be able to practically build just a basic web application. But this week 3 is kind of in this odd little area, and it's very much the kind of things you would go hardcore on in like a 4-year CS degree. Which that degree often doesn't teach you the practical stuff. And the main reason is because these ideas will show up on tech interviews. Not always. We get different feedback about what kind of interviews people see, but we wanted to introduce this concept of why with data structures and include LeetCode as this model of the tech interview. And then there's some other stuff here where I teach a little bit about how computer memory actually works, because that's kind of essential knowledge to understand the why for a lot of these data structures. And then I slimmed it down from what it normally is, where we're really just covering arrays and linked lists in depth, and we'll get into what these are. You may feel you are familiar with arrays already because Python has lists and Python has lists and JavaScript has arrays. But we get into the distinction between kind of what a data type is in a language and what a data structure is, because they are different things. And even when they share the same name, it's not quite the same thing. And then there's a slide deck here that covers everything. So I'm going to be doing everything from the slide deck today, but still, all the other data is here for reference. And then at the bottom of this page, we have the assignments. And then as you can see on the left here, we have like code examples. So I have some array stuff and some linked list stuff, just, an actual implementation, because seeing an implementation of linked list can be very useful. But yeah, I'm going to click on this data structure slides link now. Having the link should be enough to see it. If you can't see it, let me know. And this is what we are going to teach from. But I'm going to open the chat quickly because I do want to know if anyone can or can't see it. See Don saying there's something in the curriculum in GitHub that says there's an assessment at the end of this week. I'm curious where that is, but if so, I believe that's a mistake. We just shifted things over a bit, where normally there was an assessment week 1 and then one week 3. So now I believe it's week 2 and week 4. So some reference to that are sometimes still around. Yep, fair enough. We can remove that. That's not what it's supposed to be anymore, I believe. Nick can clarify. But yeah, for now, let's talk some data structures. Okay, intro to data structures. So this is to what I was saying before. Most of what we teach at Code Platoon is what I would call software development, which is the practical art of creating useful software applications. That includes most of what we teach, including things like learning languages like Python and JavaScript and SQL, which is actually a language. That's what that L in SQL stands for. I think it's I'm going to get it wrong, but it's something query language, semantic query language. Libraries and frameworks, so things like Django and React that are built on top of those languages, and they help you accomplish more in them for specific tasks, like with Django, writing a backend, writing an API, with React, writing a front end that does, interesting things. And then we even talk about, different paradigms. So things like OOP, that's technically sort of still in the language area, But it's a specific approach to doing things that's popular enough that you see it in frameworks, and that's why it's worth mentioning, even if you don't end up using it too often on your own. What we learn in Data Structures Week is straight up computer science, which is the study of computers from a mathematical perspective. And computers did start out that way. They're very useful now, but it's easy to forget, or perhaps you don't know, because why would you know this, that the first computer was invented 10 years before the first physical computer was invented. What does that mean? That means Alan Turing came up with the idea of a computer to solve a specific math problem that is so hard to understand. It's, we can barely, it would take, it's like, that's a whole 3-month class to get into it. But really, it all started out as math, because it is math. And it just happened to be that it turns out you can make a physical one of these, and that those end up being useful. And then you fast forward, 60 years, and something like TikTok exists, which Alan Turing was not necessarily thinking about. I wonder what he would think if he could see it. And he's like, oh, this is, they made it really good, and this is what they're using it for. But yeah, that when you think of it in this purely mathematical way, you kind of think of different things than we do over here. You think of things like data structures, which are specific ways you can organize data that give you certain guarantees. Algorithms, which are always tied to data structures. So if you have a linked list, well, that's a way of organizing data. You might ask a question like, well, how do I walk through that linked list? How do I remove something from that linked list? How do I, this or that? And what are the guarantees? And we'll get into that. And then the guarantee thing is what we call complexity analysis, which is a really big, scary sounding term. But basically, it's the way of saying whether something, whether a data structure or algorithm is efficient in a certain way or not, in a way that is purely mathy. So it's not necessarily measuring things in time. It's measuring things in like how many steps it takes to do that. And that's always in relation to the input size. And it's a little odd. You'll see it as we come to it. Doing it for real can be hardcore mathy, but the good news is that you really don't have to learn that math. You can learn how to see it without like getting into math. You can kind of see. I'm probably talking too much about it. We'll see it in real time right now. Just try to move the chat away. Yeah. So why do we, if coding boot camps generally focus on software development over computer science, why are we teaching this at all? Well, the reason why we focus on software development more than computer science is because that is the practical skill. That's the skill you will actually use on the job. So why talk about computer science? It's odd because the tech interview is designed around it. That appears to be changing over time. But the tech interview for a long time has been designed around these computer science topics, such that when I got my first job, I demonstrate, I did like high-level tech interview stuff and demonstrated I could do it. And then I actually got the job. And then day one, it's like, okay, learn JavaScript, learn HTML, learn CSS. And I'm like, I don't know any of those. And so it's the very opposite of what you do here, where you learn the practical skill here, but we don't spend as much time on this thing that is sort of this arbitrary jump through hoops interview thing, whereas I spent all my time on that. But the reason why they do this, they're not just trying to punish you. The whole idea of computer sciencey topics, data structures and algorithms being central to the tech interview is because it doesn't matter when you ask these questions. The nature of these questions is they're prior to a specific language or a specific domain like web development or game development or something. And so it doesn't matter what language the job might be asking you to know or what sort of things you might be doing at the job. These same questions can be asked to anyone at any level, and they tell you something about your ability to solve problems. They're basically very formal problems that we already have the solutions to, that can be analyzed so precisely that it's math. So there's lots of platforms that kind of mock this approach. But the one we use at Code Platoon is called LeetCode. And to get a sense of how it works, I'm going to open up one of these problems and we'll look through it. So here is this problem right here. And I'm going to see if I can open these side by side so we can continue to see both of them. Looks like we want a little more here. But yeah, so this problem right here is called Twosome. You can see over here, it's an easy problem. As I say here, you sign in with your existing GitHub credentials. So you do want to sign in, otherwise you can't actually run anything, which is important. But yeah, so the first thing to note, I linked to this one, Twosome. It's literally the first question on all of LeetCode. If I were to look at all the problems on LeetCode, there's a lot of them. I doubt this is even all of them. But you see there's a lot of them, and they break up into easy, medium, and hard. And they really mean it in that medium questions are pretty hard, and hard questions are like insane. And easy questions are hard. So it's like, don't be intimidated by this, or just like, you have to get used to it that these are hard problems that are basically every single one is a little puzzle. And all you have to really know in programming it's actually provable. Conditionals and loops are all you need to know to accomplish anything. So it's not special knowledge necessary. It's just, how do you actually solve these problems given their very specific requirements? And they'll often seem very contrived. Like, why would anyone ever want to do this? And the answer is because it's a LeetCode problem, because it's designed to test if you can solve something and analyze it in a certain way. But right, this is an easy problem. And I'm going to click. Oh, I can't seemingly. Okay, I can go up and down like that. So the whole point of the slides right now is just to show this. So I might as well just show this while I do it. But we want to just learn the interface of LeetCode, because it's, this useful platform that, we can only teach you so much about data structures and algorithms. But this site, if you practice problems, you can cover everything. So here on the left, we have the description panel. You see there's some other things here. Like if I click editorial, I think that's probably paid content. Maybe not. Yeah, I think I could just watch this video and someone will, for 12 minutes, walk through this video with, a really solid solution. So like, there's good content here. I think they try and get you to pay for stuff eventually, but as you can see, like they really break down the problem if you get into it. And then, these are all types of solutions people have because they like getting upvoted, I guess. And then this is for when you submit yourself. So this is how many times I've done this problem. But that's usually for the sake of something like this. But yeah, this description panel is going to tell you lots and lots of stuff. At first, it's going to tell you just what is the problem we're asking you to do. So you read it and you say like, okay, given an array of integers nums, and I should show you that normally if I switch to another language, you'll see they don't give you code. They just give you something like this. So they give you the name of the function and they give you the inputs. And then if you run it, something happens. And in this case, if I were to say like return 1, well, that's not going to be the answer most of the time or ever, because it expects a list of numbers. But yeah, it's giving me an error, but it did work enough. I guess if I wrap these like this now, if I run this, it's just telling me I failed all these cases. And we'll get to this in a second. But this is what it gives you to start. And it's telling us, we have this function Twosome. It's given an array of integers called nums and an integer target. And this stuff up here is just to tell you what the types are, a little bit more about what it expects as input output. If your language doesn't natively support types. It says you can assume there's exactly one solution, so that's going to matter for this example. And then if we look through, we have these, input-output examples. So the nature of this is telling me like, there's always going to be one solution. And in this integer of nums, if I look at 2 of them, they should add up to the target. So like I look here, you can start to even see your own algorithm in your head. You say like, okay, well, let me look at the first 2 numbers and add them together. Is like, okay, that's 9. The target is 9. Oh, wow, that's the answer right there. I just returned 0, 1. Okay, here, I might add 3 and 2 together. That's 5. That's not equal to 6. Okay, well, now I need to add 3 and 4 together. That's 7. That's not equal to 6. Okay, now let me try adding 2 and 4 together. That's 6. That's equal. Okay, I return those two indices. And, just another example here. And those examples are there to just give you a sense of what the problem actually is. And you'll actually see that if you run it, they give you some test cases by default, and those test cases will match the input-output example. So it'll have nums, it'll have target, and then when you run it, it'll tell you whether you got the answer right or not. And in this case, I got it wrong, and it's actually showing me how I got it wrong, which is pretty cool. So, if I got it partially right, it's telling me, yeah. And right, so over here is the coding panel. That's where you can write your code. So you write your algorithm here. You don't have to worry about how you're getting the input or, sending the output to the terminal or anything, but you can write everything here. And then you click that run thing. It takes a second to run. If you have an infinite loop, it will actually catch that and stop after a while. There's a lot to it. You can add your own test cases. You can remove test cases. So I could say, maybe I'm going to have my own version of this test, and I want to know when I have, 12 or something. And if I run it, I could see how my thing performs against that. And my thing should fail because it's not taking anything into account, basically. But I would imagine the right answer would be 11 and 1. So 0, 1, 2, like 2 and 4 is the answer. Yeah, there you go. What else? This section here, the follow-up, we'll get into that in a second or a little later, but this constraints thing is sometimes useful. It's basically telling you what you have to worry about in terms of numbers getting too large or too small. So it's saying like you never have to worry about this nums input being less than at least 2 items, but it could be a gigantic number of items. And then nums I, so the numbers contained in that nums array, they're definitely numbers, but they could be like a very, very small or a very, very large number, and same with target. And that generally will matter less unless you're using a specific language like C, where you really have to care about representing the number. But it's still, worth reading those constraints. And this constraint is unique for this problem, but only one valid answer exists. Tells us that we're always going to have exactly one valid answer. So the input is specific. We're never going to have a situation where it's ambiguous, where it could be something like, maybe I'm trying to think 2 and 7 and 3 and 6, and let's say my target is 9. Well, 0, 1 is an answer, but so is 2, 3. And so theoretically, either answer should be accepted, but they're telling us that's never going to happen. It's always going to be there's exactly 1. And there's never going to be 0. So you'll never be in a situation where it looks like this. And let's just say it looks like this, and this is my target. And then what's the, return in that case? We don't know. Okay, but the goal here is not to solve it necessarily, but just to keep walking through the LeetCode stuff. So that was our description panel and our coding panel. And you'll see up here, you can actually choose your language. So that's pretty important. You're generally allowed to answer these questions whatever language you want. After you come out of this course, you're likely going to want to answer it in JavaScript or modern Python. You'll see Python 3 and Python are separate. So Python 3 or JavaScript or perhaps TypeScript. But all that's going to do is give you oh, I see I answered it in TypeScript at some point. All it's going to do is give you, if I go to Go, for example, it's just going to give you that stub where you can start writing stuff. And then you fill in the rest. And interviewers will generally be explicit with you if they want you to solve it in a specific language. Otherwise, it's really up to you. So let's say I did this for a while and I came up with a solution. It's sort of like you can start writing code and then you run and you see if you pass test cases, and then you go back to the drawing board. And you'll notice I can even do things like, let's say I'm trying to solve this and I'm saying, okay, for I in range len of nums, maybe I want to print that, right? So I'm going to say print I. And this is getting a little ugly because I have the comments in there. If I make this a little bigger, you probably see it, but might look a little nicer. Let's say I want it to print I, right? And then I run it. What? Invalid test case. Oh, right. That's amazing. It's able to catch that a test case is invalid. Okay, we're going to try that again. Still an issue. Oh, because I changed this one. Okay, we're just going to have these two test cases. I believe you could always say reset test cases. But you'll notice here, I actually printed, I was printing each index as I walk through it. And so printed 0, it printed 1. And then I can look at the other test case, same deal, printed 0. Oh, just printed 0. I guess that was enough for it to tell. Either way, you're able to print things to standard out. And as a result, you can actually, help yourself debug without just using that return statement. So it is pretty flexible in that regard. And in this case, if we want to analyze my algorithm, what I came up with, I said, okay, let me iterate through each index in the list. So because I care about the index, I'm going to do it with range, len, nums. And then for each one of those, I want to check each one after it. So like I want to look at 0, 1, 0, 2, 0, 3. And then when I'm done with that, I don't want to look at 0 again. I want to look at 1, 2, 1, 3. And so this is how I do that. I go from range, whatever I is plus 1 to the n. And yeah. And okay, so what that is going to do is that's going to give me, 2 indices at a time from the start. And then I'm going to add those two together. So I'll add like, whatever's at 0 and whatever's at 1 together. And if that matches the target, I return ij. If not, I continue on. I look at the other ones. And eventually I'm going to get a solution because of how it is designed. But I just decided to add this in at the end where I say, if I don't get a solution, return the empty list. Why not? Okay, so let's say I get that far. As you see here, I'm saying run early and often. Print statements will show up there. You can add samples if you want. When you feel good that you have your solution, which means at that point you're passing all the standard test cases. That's enough reason to say you think it's good. So in this case, I'm passing all the standard test cases. Now I can hit submit. When I do that in the background, it's going to run against way more test cases that it doesn't show me, but test cases designed to kind of touch on all the possible edge cases. And you'll see here, it gives me this like analysis screen. So it's saying, this is my solution. I think if I'm like, as it's showing me, I've actually solved this a couple of times in a couple of languages. It's even giving me a next question I might want to go to. I think the green means easy, the orange means medium. And if I look at this, the important point is that I've never looked at the details. Yeah, so it's actually like showing me runtime and memory. And this is where we start to get into the complexity analysis thing. So this is all about how, like performance, basically. And there's two things you can care about in performance. First, how fast did it run? And two, how much memory did it use? It's good to know about both, but runtime tends to be the thing people care about more. We talk about both day 3 of data structures, but just looking at this right now, you'll see I only beat 15% of people. That doesn't seem great. And it seems like a lot of people got over here. So it's like, there's a lot of people that took a fair amount of time. And then over here, a lot of people seem to take a very short amount of time, over half. So that seems like kind of the goal. And actually, if we X this panel out right now, it'll bring us back here to the coding section. And then if I go back to description and I scroll down, you see this up here. It says, follow-up. Can you come up with an algorithm that is less than O(n) squared time complexity? So that should not be familiar to you yet. What does that mean, right? We get into this much more day 3, but we do cover it a little bit today. This complexity idea is essentially saying it's measuring things in steps, and it's steps relevant to this input n. So basically you can say, okay, well, the thing that changes, the thing that can grow in this problem is the length of nums. So nums could be of length 10, it could be of length 1 billion. And that will obviously affect the problem, because if we're running this algorithm and the answer is the last two indices, it's going to have to look at everything beforehand. That's going to be a lot of steps, right? How many steps is it going to be? Well, I'm looking at n items, and for each n items, I'm looking at n minus 1 items. And because I'm doing that for each one, that's n times n minus 1. Without getting into the details, that counts as n squared. That's as if I did n times n. And so if I had 10 items, I would have to theoretically look at 100 different pairs to find the answer. And if I had 1,000,000 items, I'd have to look at 1,000,000 squared pairs to find the item, to find the answer, theoretically. And so this O here, the big O, means worst case scenario. That's what we care about. In the worst case, in this case, the worst case would be it's the last two indices. How long does it take? And what they're asking me here is basically, can you find an algorithm that doesn't need you to look at every pair of indices? Because every pair of indices, that's going to be O(n) squared time. And you can kind of tell that colloquially, because if you look at a for loop and there's another for loop inside of it, that's probably n squared. For n things, you're doing n things. And they're kind of saying, how else can you do this that, is faster maybe? And I will leave that open to you. Like, if anyone wants to say, maybe like something they see, another way they can do this, feel free to contribute. But I will say it's like tricky. Like, I think, I don't know if I got this one on myself or I learned it, but when you do these problems, you eventually learn tricks. So can anyone think of like another way you might be able to tell if something's faster than what we did with the pairs, to tell if two of these numbers add up to 9?
I think Francisco showed a solution where it used a dictionary and only one loop.
Okay, did he share it in the chat?
I think he showed us. I think it was like, so I think we had a dictionary, and then for each value, we would, if it wasn't already in the dictionary, we would put it in the dictionary. And basically, if we found a value, we would check to see if it was in the dictionary, and then see if like the value, or like I think it's called like the complement was in the array.
Yeah.
And I think that's kind of how it was done.
Yeah, that makes a lot of sense. As in, this target is never moving. It's 9 the whole time. And so the complement to each one of these things is like, the complement to 2 would be 7. The complement to 7 would be 2. Doesn't make sense to complement 11 and 15 because they're greater than 9. But the idea is you can just go through one thing of the loop and you find out all the complements. And then if you are using a dictionary, you can have instant lookup to say, is that there or not? So yeah, I mean, I would have to implement it to see for sure, but you could see how that could get us a better runtime. And in fact, if I looked at solutions, I bet that's the best way. I just do Python 3, and then we click on one of these. Fire. This one's Fire. That's an official thing that says this is a good one. I'm kidding. This guy just wants us to read his. Please upvote. I love how people, no matter what platform, people like love the likes. Oh, he has a video. So people really use this platform, right? So what is he doing here? He's using this array, and then he's saying, for ij in enumerate num. So can anyone tell me enumerate? That's going to give me the index and the value. Yes. I think so. Yeah. I wouldn't have named these ij because it gets pretty confusing. But yeah, he's getting the complement, which he's calling R. I hate his naming of things. And then he's saying, if the complement is in the dictionary, then return the current index. Yeah, this is pretty complex, but I guess it works. And then if you were to look at his performance, I assume it would be better. And he explains how it works here. But to the point of like the using the object, what you learn over time, which can be hard to do immediately, but like this stuff here is kind of this like hidden language which says like ON2, okay, well, you used a doubly nested loop. Is there some way to get around that? And what you learn is that while it's hard, I don't think we necessarily get around this week, perhaps a little bit day 3 to talking about why a dictionary in Python or an object in JavaScript is, what we call constant time lookup. It's not based on the input size. The fact that that is a property kind of tells you that when someone's like, can you do this better? You're like, oh, maybe there's some way I can, use an object to help me out because that's like free in a sense. And yeah, it's you learn it over time. There's kind of no other way, but you really don't have to understand the math behind it. You just have to sort of learn when you want to, reach for a certain tool. So coming back here, the point of that was just to sort of introduce you to this idea of LeetCode, and the assignments today are actually just LeetCode problems. Start doing this again. Yeah, I go into this a little more here about what the O and the N means. We do get into this a little more today when we talk about specifically arrays and linked lists, but the big thing to take home right now is that the O means worst case scenario. We want to think about what takes the longest to run, what the absolute worst case scenario is, which will often be, oh, it's the last indices, or it's something like it's just not there. So you have to search everything to find out it's not there. Or let's say it's a sorting algorithm. Very often the worst case scenario will be it's in reverse sorted order. So it's as unsorted as it can be. But right, you're trying to figure out what the worst case scenario is. And then the N means we care about it relative to the input size. And that's not always clear what the input size is, but you want to be concerned with the input size that grows the fastest or grows at all. And in this case, that's N, meaning the length of this nums array. Okay, so that's enough LeetCode for now. We're going to take a step back now. We're going to take a step away from sort of, practical language stuff and software development, and we're going to come back to computer science. And in order to make sense of any of the stuff we're going to talk about today, it's helpful to know a little bit about how computer memory works, which we've not really discussed. Because the nature of our program, the nature of computers as they are, is that they build up and up and up, and you often don't understand what happens under the hood. And I can tell you even now, what I'm about to teach about computer memory is not really how computer memory works. It's how we can think about it in a useful way, but this is how it works in the most naive way possible. And companies like Intel or AMD, whoever they are, their whole thing is trying to optimize on these, basic hardware things. And as a result, the reality is way, way more complex. But thinking about it this way at least lets you start thinking about things, because chances are you're never going, there's like 100 people in the world who actually understand how, the different levels of memory and caching that happen in a modern processor. Yeah. So for the sake of understanding complexity analysis, we want to understand this idea of like N and the input size. And memory is an important part of that. So we think of memory as as contiguous blocks of identically sized, slots or, mailboxes or something. Literally, the guy who came up with all this guy, John von Neumann, his example of what a computer is way before computers existed was basically you have like 50 mailboxes in a row, and someone puts something in the first mailbox and someone can take something out of the last mailbox, and everything in between is, the computer can manipulate those other mailboxes. It can take something from the first mailbox and move it to the third mailbox. And just using that, it's able to, that's a computer, just the 50 mailboxes in a row and something that can move things between them. Like let's say a a single number on a letter in that mailbox. But right, so we're going to think of it as these contiguous blocks of memory. Contiguous meaning all right next to each other. So it's just one long row of things that are the same size. And because they're the same size, it's almost like we could think of this as like, this is some weird street, some weird town where there's only one street, and it's not even on two sides of the street. There's only homes on one side of the street, and every single plot is identical in size. So let's say it's 32 feet, right? So every home has 32 feet in length, you know, horizontally. And let's say, you know, it's a square. So it's exactly the same either way. But then because of this, how might you tell what the fourth home on the block is? You could call it the fourth home, but the way computers do it is they actually measure it in bits, because bits are the smallest pieces. But we kind of care about, you know, these larger units called bytes, and we might even put some bytes together. And so if I have a computer, I might say like, okay, every piece of memory that I care about, every unique slot holds 32 bits or 4 bytes. And so I can measure it that way, where I say, okay, the first one starts at 0, the second one starts at 32, the third one starts at 64, and you could, like, even talking there, I got a little confused because you can start to see why computers are 0 indexed often, because 0 starts at 0, 1 starts at 32, 2 starts at 64. And this numbering scheme is not essential. So this is an example of what we would call a 32-bit architecture. Nowadays, it's very common for things to be a 64-bit architecture. But all that means is that in order to make working with the computer sort of standard in a lot of ways, everything fits into 64 bits or 32 bits, whatever it is. And so like a number is always going to fit there in that, 32 bits. So an integer will fit in 32 bits, a float will fit in terms of 32 bits. Strings are kind of made of characters, as we'll see, but a character fits in 32 bits. A Boolean fits in 32 bits. And you might say like, well, that's overkill because a Boolean could fit in 1 bit. It's either 0 or it's 1. Why do you need 32? The whole idea is just that this standard unit, it's always 32 bits, helps us in terms of traversing this, because if we save something that was 7 bits long, like an ASCII character, and then we save something that was 1 bit long, like a Boolean, and then we save something that was 32 bits long, like an integer, and something that was 64 bits long, like a big int or something, we would quickly get into this place where we can't use that number scheme to know where we are. And that is going to be an important attribute, that we can use that numbering scheme. So just to show this idea of memory addresses, this actually exists in Python. If I say something like x equals 1, I created a variable Python knows about, and I set it to the value 1. If I say ID x, that gives me this crazy number, which I don't even know without the parentheses, but it's a really big number starting with 4. And that's the actual memory location of x. So that's telling us literally physically on the computer, that's where I stored this value just now. And then you could also use this function hex, which is going to turn into hexadecimal. The only reason I'm showing that is because often when a memory address is printed, to save space, because this number can get so large, they start using this thing called hexadecimal, which is still just a number. It's the same number as this number, in fact, but it uses letters to make it shorter. And we're really not going to go too much into that, but it's worth knowing about, because you will start to see this in errors, and now you'll be able to recognize it and say, oh, that's telling me a memory address. That's useless for me, but at least I know it's trying to point me to exactly where it's happening, because in some languages that might matter. Okay. And what I said about these memory addresses, 0, 32, 64, whatever it is, that is what fits into one of those slots is always going to be a primitive. But in reality, certain things we think of as primitives in like Python, like a string, they're not really primitives. They're complex in that they're really collections of primitives. So for example, a string is really a list of characters. And Python goes out of its way to say, you're not worrying about characters, you just think in strings. But in reality, the string looks something like this in memory. Each slot takes up one character. And so if you have 5 characters, that takes up 5 slots in memory, all one after the other. Okay, so I'm going to look at time quickly. It's 8:42. I think we can go a little longer. We're going to take a break, certainly by what is 10 a.m. CST. Okay, I should stop for a second. Questions, because I've not been asking for questions. And there's a lot, I know.
I have a question. So, like each character in a string, like I heard the minimum size or whatever for each character is a single byte, but it has to fit like in a word basically. So it can only access every 32 bits.
So in actual, yeah, this is where it gets complex, because if you really cared about how much space an ASCII character took up, an ASCII character fits in 7 bits. But that ends up being that using numbers like that makes it so that you can't say, like, with this system, I can say, where's the first one? 0. Where's the fourth one? Oh, 32 times 4 plus, 0 where I started. And that way you could instantly jump to that 4th character. That's what indexing is, as we'll get into. Because you want to do that, it doesn't matter that it only takes 7 bits. We store it in 32 bits. And that's because this is a 32-bit architecture. Modern computers tend to be 64 bits. It means it's using all 64 bits in that single slot to put 7 characters, or 7 bits that represent that one character. So there ends up being a fair amount of wasted space. But that isn't really a concern, because it's much more valuable to have this regular system of, basic things fit in one slot. Is that helpful?
Yes, thank you.
I'm having trouble understanding the part where it's putting every letter in a different square. Like, if it all fits in 0 to 32, why are they separated?
It doesn't all fit in 0 to 32. So
It doesn't.
No, like if I were to, it's a little strange. I mean, it tends to be a fair amount to go into, but let's say I'm going to go back here, and I'm going to Google quickly ASCII letters binary. So everything in the computer ends up just being 1s and 0s. And so if I were to open it up like this, so I want to store hello in memory, right? And then I look here and I see, oh, capital H, that's what this looks like. That's just the H. So just H equals this, and it's 1, 2, 3, 4, 5, 6, 7. They're representing it as 8, but that first one is always going to be a 0. And I can look it up for the other ones. Just for the sake of completeness, I can say, like, okay, this is my E, and then we'll get 2 for the L. That's nice. Where's my L at? And you can see how very quickly this is not very readable for a human. And then where's my O? So, this all looks kind of the same, but so I have these 5 characters here, and 5 times, in this case, they're representing as 8 because computers like working with powers of 2. So 8 is a single byte. 8 bits is a single byte. So, let's say I wanted to include that leading 0. 1, 2, 3, 4, 5. 5 times 8 is 40, right? Yeah. So basically, that all cannot fit in one 32-bit slot. And so what we do instead, we say, like, okay, well, 0 to 32 is just going to be this number with a ton of leading zeros. So however many leading zeros I need to be, 8, that's how many leading zeros. So it's like 1, 2, this should be 8 zeros, right? And then I want this how many times? 1, 2, 3, 4. 4 times 8 is, no, I want that, right? I want 3 leading. That's confusing for me. 8 times 3 is 18. 26. Yes, I think I do want that last one. So basically this represents just the H. And most of those things are just zeros. We're just not using it. And then same with this next one. We're going to do that same thing with all of these zeros. And so like these are now representing, this is a, 0 to 32. Oh, I already wrote that up there. So like this is 0 to 32, and then this is going to be 32 to 64. And then, 64 to what, 96 or something? It's harder to do. So basically in computer memory, it's going to look at things 32 bits at a time. And it's a 32-bit architecture. And so it looks at this one, it reads all those zeros. It's just they don't count towards anything. And this represents just an H. And then this is the next letter, and this is the next letter. But importantly, if I wanted to get that fourth letter, I could just jump there. I could just say, okay, wherever H is, which in this case is 0, go there. And then I want the fourth one, so add 4 times 32. And then that's the exact memory location where this one starts. We'll talk about this a little more when we do the array stuff. It's not important that you understand it super deeply because we can't go into it super deeply. And even what I'm saying is a simplification of what it actually is. But that's enough to give you this intuition about how essentially that you can jump somewhere. And you can only jump somewhere if it's a mathematical equation to say like, oh, I want the 100th thing, 100 times 32. Okay, now that's going to be 100 slots forward. Okay, is that helpful? I'm looking in the chat right now.
Yes, it's helping a lot.
Okay, great. Yeah. And that's part of the reason we rewrote this stuff last week is because a lot of times data structures, they don't make sense unless you have this low-level intuition. And so it's better to learn fewer of them and get the intuition than to just like throw a lot at you and you're like, how does that actually work? Okay, so the next thing we're going to talk about is arrays. And the whole point of everything up till now was that we could start talking about it. I think now is an appropriate time to give a break and we will come back. Francisco, are you here?
Yes, I am.
We generally do 10-minute breaks, 15-minute breaks. What's the consensus on that?
I usually go with 10-minute breaks unless I've gone for a while, then I just do 15-minute breaks, but it also depends on how the class is doing. I usually look at their faces.
Yeah. Well, all their faces are just beaming. It's really incredible. It's like looking at 39 suns.
Just keep pushing them. They don't need a break. No, I'm just kidding.
Exactly. Yeah, no, that's what their faces are telling me. You're right. Just read the faces. Don't ask them.
Yeah.
No, it's 8:50 right now. Let's give you 10 minutes. I'll stay here, but everyone has a 10-minute break. Sorry, it's 9:50 CST. We're going to come back 10 a.m. CST, and then we'll continue on with the race. Cool. I know you can see.
So those are called words, right?
1 second. Though you're saying this, the like 32 on a 32, the slot is called a word, is what you're saying.
Right.
Yeah, technically that's a term you can use. Because it's different on each system. Way to talk about different systems, like one might be 8-bit and one might be 64-bit. That 8-bit on an 8-bit computer is the size of a single word. On a 4-bit, 64 is a single word. And you generally don't deal with anything smaller than a word because without that, base unit, you can't guarantee this consistent, structure.
I heard about like half words. Does a computer ever deal in half words?
Well, the thing is, like, if we were to get practical about it, that's where it changes. So like if I were to look up something like, Intel x64 architecture, like they definitely have that concept. Because that's definitely useful at times. But understanding it, I don't even know where to begin. Like, like I'm trying to figure out how I can find out their. Like you see here, like basically they understand this. They have different things. It's not that, oh, you're on 64-bit computer, so everything's 64 bits. They know how to
Right.
think in smaller bits.
Mhm.
It's just that detail is for them. It's not for you, the programmer, because you could easily mess things up.
Mhm.
I don't know that this is really explaining it, but I guess Intel x86 architecture half word. I mean, yeah, I really don't know how to answer that. It's just it gets like hyper complex when you break it down. Like they know about different things, and the different things are organized in certain ways. So there's lots of data being packed into that 64 bits. It's not ultimately
Right.
that piece of data.
Mhm.
But it's incredibly complex to understand how they're doing this.
Okay.
Yeah, processors are just rocks that we tricked into thinking with lightning.
Right.
No, but for like there is this thing where in school, even if you take a whole class on this, you learn
Mhm.
a processor that's essentially a dummy processor for the sake of teaching, because modern stuff is so optimized that it's so hard to understand, and it's not useful as a learning tool. So like this isn't something that is helpful for understanding how understanding how a processor works, because there's so much going on there for the sake of efficiency.
Mhm.
Sort of like in the terms of understanding a processor in its basic form, you might have this analogy to like laundry, where you say like, oh, I have like laundry, like dirty clothes, and then I put it in the washer, and then when it's done, I put it in the dryer, and then when it's done, I fold it. And like that's this like process that it follows. And then a modern processor is like this thing that says like, hey, but what if you have multiple loads of laundry going at once? Like you could be washing something at the same time you're drying something. And it's much more about like not just how does it work, but how do you create as optimize a chain of command, and how can you know early, how can you as early as possible know you don't have to do some other work. And it's
Talking about like different threads and like thread pipelines and stuff
yeah,
like that.
exactly right. You got multiple threads in there. Like it's just so much to think about, and I have no idea what any of it means. Yep, a lot going on. But I mean, yeah, like if we wanted to see like a simple one, it's like MIPS processor. This is the one they teach you on, but it's like the last time it was used was in like cell phones in like the 90s. It's still complex, but it's
Mhm.
like at least not like hyper optimized. I still don't understand this. Um, yeah, not sure how I can actually help you here. But yeah, that concept of word size definitely exists, and you could have half words, you could have double words, you could have there's times where that's useful because it all does break down to bits, and there's sometimes where caring about just a single bit might matter. But that requires a level of understanding of what's happening under the hood that they don't really want the average person to have to know.
Okay. Thank you.
All right.
Francisco,
Hey, what's going on?
I had a question about test case 15 for the assignment.
Yeah, what's up?
So, can I share my screen?
Of course. Are you gonna show code about the assessment? If so, then no.
Okay, never mind, I won't then. But so in test cases 12, 13, and 14, we're adding a customer to the customer type maker, and that's making an instance of customer. And so we're making 3 instances of customer.
Mhm.
and we start with 6 customers, but it's asserting that the customer.keys is equal to 8 when we just added 3 customers, so it should be 9. So I don't understand.
Yeah, so test 10 and test 11 are the ones that are
Yeah.
actually adding a customer into the amount of customers that you have, not 12, 13, or 14. 12, 13, or
So
14 are only returning a new instance of a specific type of customer. But that's not supposed to be added into your storage of customers.
okay. But when in 10 and 11, when we close the program at the end of it, it's closing like the instance of so it resets my customers back to the initial state. Should that
So 10 and 11, once they're done running your program, although they're done running the run the store method, it doesn't, oh, where did you go? You stopped, oh, you stopped sharing. Yeah, although it stops running the run the store method, it still retains the information because it's not done running the Python file. So all of the
Mhm.
information that's in there is still current.
Okay.
Does that answer your question?
Um
Yeah, we may have to break out one-on-one and maybe talk about it. Once I get to your assessment, I'll ensure to take a look at test 15 and give you some good feedback.
okay. Thank you.
Of course, no problem.
Hey Ben,
Yes.
I've been reading this book that Guillermo recommended, the code book.
I've heard of it. Yeah.
It is really good and it goes in depth on a lot of this, basically all the stuff you're talking about.
Yeah. Yeah. I mean, I'm sure I would learn stuff reading it too. It's I'm trying to find you guys again. I can't seem to see the screen anymore with the Zoom. Zoom is so weird. Give me a second. Yeah, I imagine there's what to learn in there. Because a lot of this stuff was figured out like pretty early on, and the design of computers is so that you don't have to know about those low-level details, because that's what kept people in large part from doing it. Like it just took so long to do the basic things because you have to think in ones and zeros, and you have to build these ideas up like one at a time. Where the heck is Zoom? I might have to close Zoom.
Yeah, I think it's you because it also says Benjamin Cohen has started screen sharing, but we can't see anything.
That seems to happen sometimes when you start screen sharing. It just like it breaks for you. Because I still see my stuff. I can still talk to you, but I don't see the outline saying I'm sharing screen. Okay, I'm gonna end this and